Learn like a pro.
All right, today we're uncovering the secret life of metals. We're talking everything from how we actually get them out of the earth to how we stop them from, well, turning back into dust. So, here's a question for you. Why does a big, strong iron fence literally crumble into rust, but a flimsy little aluminum can seems to last forever? It kind of feels backwards, right? Well, the answer isn't about strength, not in the way we usually think. It's all about a hidden chemical power struggle that starts deep inside the earth. Okay, first things first. Most metals, they're not just lying around as shiny nuggets waiting for us to pick them up. Nope. They're actually trapped inside rocks. We call these rocks ores. And in there, the metal is chemically stuck to other stuff, usually oxygen or sulfur. So just getting the metal out, that's the first big battle.
So to understand how we actually free these metals, we need to know the rules of the game. And in chemistry, that rulebook is something called the reactivity series. Honestly, the best way to think about it is like a chemical pecking order, a power ranking for metals.
And this really is a power ranking. The metals at the very top, like your potassiums and aluminums, they are super reactive. They cling to the oxygen in their ore for dear life. Then you've got the guys in the middle, like iron. They're a bit more chill. And the ones at the bottom, they're basically loners. And believe it or not, this one simple ranking, it dictates everything that comes next. Okay, so this ranking isn't just some abstract chemistry thing. It's totally practical. It tells us exactly how we're going to get that pure metal. It tells us if we need a bit of clever chemistry for the middle-of-the-road metals, or if we need to bring out the big guns, pure brute force for the ones at the top. All right, let's start with those middle-tier metals like iron and zinc. For them, we can use a really clever trick, a chemical swap. We bring in carbon, which is great because it's super cheap and there's tons of it. You see, in a chemical showdown, carbon is actually more reactive than iron or zinc. So when you heat them all up together, carbon basically just swoops in and steals the oxygen away from the metal. It's a fantastic little trick. But there's a small catch. You can't just toss any old ore into the furnace. See, carbon is a bit of a picky thief. It can only steal oxygen. So if your ore has the metal stuck to sulfur, what we call a sulfide, you have to do a step first. You've got to roast that ore in the air. This forces the sulfur out and lets oxygen in, turning it into a metal oxide. Then, carbon can do its job. And here's exactly what that chemical swap looks like in action. You take your zinc oxide, you mix it with carbon, and you heat it up. Now, because carbon is the more reactive one, it just muscles its way in, snatches the oxygen, and makes carbon dioxide. So what's left behind? You got it. Pure, shiny, metallic zinc. It's a really neat and simple switch when you think about it. But this clever little trick has its limits. When you get to the real heavyweights at the top of the reactivity series, we're talking aluminum here, carbon just isn't strong enough. It's completely outmatched. The chemical bond between aluminum and oxygen is just so incredibly strong that carbon can't break it. So for these guys, we have to call in the cavalry, and that means the brute force of electricity. So you end up with two totally different strategies, right? On one side, for those super tough bonds like an aluminum oxide, you need the raw power of electrolysis to literally rip the atoms apart. But on the other side, for the less stubborn ones like iron oxide, that little bit of chemical finesse using carbon is all you need. And the setup for this is just huge. First you have to melt the aluminum oxide, which takes insane temperatures. Then you pass this massive electric current through the molten liquid. What happens next is like a magnet. The negative part, the cathode, pulls in the positive aluminum ions, and they collect as pure molten metal. At the same time, the positive anode pulls in the negative oxygen ions, and they bubble off as carbon dioxide. It's a pretty intense process. And yeah, as you might guess, this brute force method comes with a pretty big price tag. Just look at the energy difference. The amount of juice you need for electrolysis is way higher than for carbon reduction. That's really the trade-off, It's the price we pay to get our hands on these super reactive and super useful metals like aluminum.
Okay, so we've spent all this energy. We've got our pure metal. The battle must be over, right? Wrong. In fact, it's just getting started. See, the universe loves stability. And for these reactive metals, that means finding their way back to oxygen. Nature immediately starts trying to turn that shiny metal back into a dull oxide. We all know this process as corrosion.
Now, when it comes to iron, we call this process rusting. And for it to happen, you need two things, oxygen and water. The stuff that forms that reddish-brown gunk is called hydrated iron oxide. And here's the problem. It's flaky, it's weak, it just crumbles away, and that exposes fresh iron underneath, which then starts to rust, and the cycle continues. It's this relentless, destructive process that literally doesn't stop until the iron is just gone. And this brings us right back to our very first question. Because here's the crazy part. When aluminum corrodes, it forms a super thin, super tough, and basically invisible layer of aluminum oxide. But this layer doesn't flake off. Oh no. It sticks like glue and forms this incredible airtight shield that protects all the aluminum underneath from any more corrosion. So get this. Iron's rust is its fatal flaw, but aluminum's rust is actually its secret suit of armor. So, since poor old iron can't protect itself, we have to step in and help. And we basically have two main strategies we can use. Think of it like this. We can either build a fortress around the iron, or we can hire it a chemical bodyguard. So the first method, the barrier method, is the most straightforward. It's basically just building that fortress. You put a physical layer between the iron and the elements. We're talking about a simple coat of paint, a layer of grease, a plastic coating, or even plating it with another metal like tin. The logic is simple. If oxygen and water can't touch the iron, it can't rust. Makes sense, right? Well, there's a catch. Because what happens when that barrier gets scratched? Now, this is where it gets really interesting. If you've got a tin-plated can, a scratch is a disaster. Why? Because iron is actually more reactive than tin, so when they're both exposed, the iron rusts even faster, almost like it's trying to protect the tin. But now look at galvanizing, where we coat the iron in zinc. Here, the exact opposite happens. Zinc is more reactive than iron, so when there's a scratch, the zinc corrodes first. It becomes the bodyguard. And that's our bodyguard strategy. The official name for it is sacrificial protection. It works simply because the more reactive metal is, let's say, more eager to react with the oxygen and water, it basically jumps in front of the bullet, corroding away so that the less reactive iron stays safe. It's a noble sacrifice, really. And this simple experiment shows the rule perfectly. Look, an iron nail by itself, it rusts just like you'd expect. But now, check this out. When you attach a more reactive metal, like this piece of magnesium, the iron doesn't rust at all. The magnesium is taking the hit instead. But then, if you attach a less reactive metal, like copper, whoa, the exact opposite happens. The iron actually rusts faster. It's a perfect demonstration. And this isn't just some neat little lab trick. This bodyguard principle is used on a massive scale. That same idea that protects a galvanized bucket, it's used to protect gigantic steel structures like ship hulls and underwater pipelines. They literally bolt huge blocks of zinc or magnesium right onto the steel. These blocks then spend years slowly corroding away, sacrificing themselves to the harsh salt water, while the incredibly expensive ship or pipeline stays perfectly safe. So as we've seen, it all comes back to that one list. From the moment it's pulled out of the ground as a rock to its final use in the real world, a metal spot in the Reactivity series really does define its entire story. And it really does boil down to a simple pattern, doesn't it? The higher up the metal is on that list, the more reactive it is, and the more brute force, like electrolysis, you need to get it out of its ore. For all those middle-of-the-pack metals, that clever little swap with carbon works just fine. So, the next time you see a crumbling, rusty gate or a shiny, sleek airplane, you'll know the secret story behind it. You'll know it all comes down to one single thing: where that metal stands in the great chemical pecking order. That ranking determines everything: the massive energy needed to create it and the constant, invisible battle it fights just to keep from turning back into rock. It really makes you think, doesn't it? In the world of chemistry, maybe reactivity really is destiny.